Hello, welcome to our channel for doing statistics using R programming. In this video, we will show how to use geometric distribution in R. So first we will talk a little about what is geometric distribution. So geometric distribution is a special case of the so-called negative binomial distribution. So we have in previous video shown that negative binomial distribution is used to model the situation that how many times trial to get several success in a Bernoulli experiment. So with a constant rate for success with a P. So for example, if in NBA match in the final, we want to know how many match the game the winning team will have to get a 3-game win. For example, the winning team can win with 4-3, 5-3, or 6-3, or 7-3, right? So in this situation, we model the how many times of match to get how many times of success. And in geometric distribution, we just want to know how many experiments you want to take to get only one success, right? So geometric only get one success, and we want to note number of experiments you have taken. And in each trial, each trial, there is a constant success rate called P. So this is the experiment situation exactly the same for geometric, for negative binomial and binomial. They are the same because they have the same constant success rate P. And they also can say they are so-called repeated experiments. So geometric distributions probability has this form P times Qx minus 1. So P here is a constant rate P because we only have one success, so there are only one P in the production. And Q is the failure, which equals 1 minus P. So here has the power x minus 1. So x can be 1, 2, 3, 4, 5, 6 for integer number, and so on. So the mean of geometric distributions, where random variable is 1 divided by P. So if you can say you have to take average 5 times to get a single success if the success rate is 0.2, right? So the average. And the variance is 1 minus P divided by P squared. So in R, if you want to use geometric distributions probability function, so there would be taken with dpqr, one of these 4 alphabets, then with an distribution abbreviation. So here D means density or probability, P means cumulative distribution function, and Q means quantile function. Quantile is actually the same with the same random variable, use different name, right? So quantile is same as the random variable. R is for the random number generation. So this dpqr applies for all probability functions in R. For any other distribution, you will have to use these 4 alphabets. And for the geometric, we'll plus the geom in distribution abbreviation. So next we will show how to do it in RStudio. So first, we'll create a random vector called xgom. And this vector has 10 variables from 1 to 10 by the gap 1. So next, you can use the geom function to calculate the probability of this random variable in xdgeom with probability for the success rate is 0.5 in a geometric distribution. Then we plot this value. So for example, random number 1, you can get about 0.25, and 2 about 0.12, right? So the probability decreases with the random number increasing, because this is the probability. You can see P is the probability success rate less than 1. So for the 1, Q also less than 1, right? For x equals 1, this part is 0, so equals probability P. But x equals 2, P times Q, because Q is less than 1. So when x is 2, surely this part will be less than x equals 1, right? And so on. So when x increase, this part will decrease. So this is for the probability. And next we will calculate the cumulative probability. We use P geom x, this vector, with the same success rate. Then plot this value. So cumulative probability, of course, is non-decreasing function of the random variable. Because, for example, if we say 6 here, so here is about very close to 1, about 0.98, for example. So what this means? This means in this geometric distribution with a success rate 0.5, you have to take 6 times, at least you can do no more than 6 times to get a single success, with getting 1 success with the probability 0.98. So in 0.98 probability, you can get a single success when you take less than 6 tries, right? So next function is QGOM. It is actually the opposite function of the PGOM. So here we will create a vector representing the cumulative probability between 0 and 1. Then we pass this vector of probability with the same distribution for the geometric. Then we calculate the random variable. Next we plot. Now this is actually the opposite. For example, 6 here. This is for the probability 0.6, the horizontal representing the probability. So between here 0.6 probability, you get very low value for the integer, because the probability for increasing this here is very low. But for between 0.8 and 0.8 and 1, it increases very fast. For the integer values increase, right? Because this part of random variable has very high probability. So that's why increase very slow here, then increase quick. And the last function is for the random number generation. We set n equals 10, which we want to generate 10 such random number. Then use rGOM function with n and the probability 0.5. Next we plot these values. So you can see the 10 number first is about 1, very close to 1. Then 2, 3, and so on. All are random number generation. You can also download the source files from this GitHub link, and more videos will be uploaded later on YouTube. Thanks for watching.